In this video, I will be talking about inverse functions. Before starting, I would like to take a look at this example. What can be said about the following functions f and g? You realize that f is represented in the first picture, seems to be taking an element, a collection of elements on the left hand side, 1, 2, 3, 4, takes these elements and assigns to some other values or elements in this other set of elements. So you can think of this as like a domain of the function f and range of f. In other words, domain is x values or input values and range y values. So you realize that it takes 1 to 8, 2 to 6, 3 to 7, 4 to 5. And then g, on the other hand, has its own domain here on the left side, takes 8, 7, 6, and 5, and then takes these values, assign them to different values on the right hand side, and that seems to be its range. So what I like to do is I like to compare one by one what these functions are doing. So for that reason, I'm gonna use like a table for input and output relationship. So for the first function f, input 1 is assigned to the output 8. Input 2 is assigned to the output 6. Input 3 is assigned to 7. Input 4 is assigned to 5. If we do the similar thing for g, input, output, if you create a table of values, you realize that the input 8 is assigned to output 1, input 7, this function assigns it to 3, input 6 is assigned to 2, input 5 is assigned to 4. So as you can see, well, first of all, when you take a look at these two tables, what do you notice? A lot of you can notice that the input of this function 1, 2, 3, 4 seems to be the output of this function, and output of this function, output of function f, seems to be the input of the function g. So as you can see, there is some kind of reverse order going on, because this function takes input of 1, 2, 3, 4, and then this function takes the input of 8, 7, 6, 5, and it seems to be that these functions have inverse relationships. And what we realize here is that domain of f is the range of g, the range of function g, and then the range of f seems to be the domain of g. So for this reason, f and g, we can say f and g has a reverse order relationship. And for this reason, we're gonna call them inverse functions. Okay, in order to illustrate this better, I'm gonna take a look at this example. I'm gonna use a slightly unconventional way to illustrate this input-output relationship. So here's what I'm gonna do. I would like to take a look at this function. But first, what I like to do is I like to take a look at, focus on the rule for this function. I like to understand what this function does. And so, as you can see, f of x is the y value or the output, and x is the input for this function. So, what I like to take a look here is take a look at the rule of this function. So what this function does is, the rule for this function is essentially, what it does is it first takes the x value and multiplies by 2, right? So multiply each x by 2. And then what it does is, and then it adds 1. So second thing this function does is it adds 1 to each 2x. Okay, that's great. So then if I were to ask you, well, how do we find the reverse operation? How do we undo this function? So how do I undo this function or this rule, right? So if I ask you that, then what you would do is, because we're going in the reverse order, the last thing you did for the rule becomes the first thing you do. So what we're gonna need to do is, first we need to, instead of adding 1 to each 2 of x, we need to subtract 1. Subtract 1. And then what we need to do is, we, instead of multiplying each x's by 2, we need to divide by 2. So this two-step operation basically undoes the rule of this original function. And then the way I'm going to illustrate that is going to be as following. So for the rule of the function, what it does is it multiplies by 2, and then it adds 1, so multiply by 2, so x times 2 plus 1. So what this turns out to be, if you like clean it up, it becomes 2x plus 1, right? So this is my function f. So here I'm gonna undo this, so I'm gonna subtract 1, so I'm gonna do x minus 1, okay? And then I'm gonna divide this by 2. I'm gonna divide the whole thing by 2. And you realize this produces a different type of function, which is equal to g of x. And that g is exactly the inverse of f. So this is more like a procedural, more like an interesting way of looking at inverse relationships. So now what I'm going to do is I'm going to provide you the formal definition of inverse functions. Let f and g be two functions such that f composed with g, you realize this represents composition of functions. Composition of functions. F composed with g could be represented as f of g of x equals x. Similarly, f or g composed with f, same thing as g of f of x equals x. If this is satisfied, then g is the inverse function of f. In other words, g is f inverse f. G equals f inverse of x. So you realize this is the notation for inverse functions. We simply put this -1 as an exponent to indicate that g is the inverse function of f. For this reason, we can say that f of f inverse of x equals x, or f inverse of f of x is the same thing as x. So this notation might seem a little bit confusing, but if we take a look at this analogy of using these sets, it might make more sense. So think of it as, say there's like an element x in here, and then think of a function that takes this x and assigns it to this element on this other set f of x or y. Okay, so what f does is it takes x and then assigns to f of x. And then think that there's another function that takes this f of x as an input and then assigns it to this other value. And if that value happens to be x, and then if this other function is called g, what ended up happening is when you compose these two functions, so going from here to there is basically f composed with g, right? Because you're applying those two rules all in one. And then if the resulting is what we get in the first place, you input x and you get output as an x, then f and g must be inverse. And so for this reason, g is an inverse. So g is an inverse of f. Okay. So then how do we verify if a function is an inverse of another function? So one way of illustrating this is taking a look at this example. So consider f of x equals 5 over x over 2. Which of the following is the inverse of this function? G equals x minus 2 over 5, or h 5 over x plus 2. So the way we can verify that is the fact that I used previously. In other words, if f inverse of f of x is equal to x, or f of f inverse of x equal to x, then you can say that f inverse is the inverse, right? Then f inverse must be the inverse function, must be inverse. So that's the idea that I use to verify inverse functions. So if you want to first use g of x, okay, so let's take a look at composition of f and g. So what I'm going to do, I'm going to compose f and g. The notation I use this, and I put x as an input, and this looks like f of g of x. So think of it as like output g's going as an input for f. And so we know what g of x looks like because g of x is x minus 2 over 5. So I put that as an input. And then here what's going to happen is, because I know the rule for f, which is 5 over x over 2, and this is my input now, so instead of x in this f, I'm going to replace x with x minus 2 over 5. So it's going to look like 5 over x minus 2 over 5 minus 2. So then what that turns out to be is, at the bottom, if you combine the 2 with that fraction, you get x minus 12 over 5. And then when you flip that, you get 5 over 1 times 5 over x minus 12. And then you get something like 25 over x minus 12. And then the question here is this equal to x? And then we realize that it's actually not, because it's 25 over x minus 12 is a different expression than x. So it's not. What that means is that g is not the inverse. So now what I'm going to do is I'm going to check with this other function. So I'm going to try composing f with h and see if that's going to work out. So instead of g, I'm going to use h of x as an input here. So then we know what h of x looks like. So 5 over x plus 2. And then I'm going to go ahead and replace that into the x of the function f. so 5 over x minus 2. Then you get 5 over x plus 2 minus 2. And then you realize 2's will cancel, so 5 over x. You flip it, 5 over 1 times x over 5. And then the result ends up being x. So what I did is I composed f with h and then ended up getting the same x. So for this reason, therefore, h of x is the inverse of f of x. So this is how we check and verify inverse functions. Okay. So then you may be wondering, how do the graphs of inverse functions look? So here what I have as this red line is the function that I just found the inverse earlier. So this is f of x equals 2x plus 1. And then this other one is g of x equals x minus 1 over 2. So you realize that previously we found that x minus 1 over 2 is the inverse of 2x plus 1. And so if you graph these, you realize the graphs would look like this because they're both linear lines. And then you realize that the function seems to be pretty symmetrical. And so here what we need to know is that these functions are always going to be symmetrical with respect to this line cutting through what we call y equals x. So you realize that inverse functions always have this relationship where their graphs are always symmetrical with respect to y equals x. And then one way we can understand this is because inverse functions have different x and y's. So like for instance, if you take a look at this point here, 1 comma 0, so x is 1 and y is 0. And then when you take the symmetrical of this point, you get, so it's like this, the other side, it's like symmetrical is right here. You notice here, your x is 0, y is 1. As you can see, x and y seems to be switched, right? Because y becomes 1 here, but then x is 1 over here. And so as you can see, x and y's are switched. X and y's are switched due to the inverse relationship. So what we're going to say is then the graphs of inverse functions are always symmetrical with respect to the line y equals x. All right. So now we're ready to talk about this, one of the main ideas in mathematics, in pre-calculus and calculus, what we call one-to-one functions. A function is defined to be one-to-one, or simply one-on-one, if each output y values correspond to exactly one input value. So to illustrate this, I'm going to use the set notations. So imagine I have some domain that has these elements, and then range that has these elements. Some function takes the first element, assigns it to the first one, takes the second element, assigns to the other one. This takes this to this other one. So if you take a look at this situation, you realize that this function, like say f, takes two x's, like say this is x1, this is x2. So realize that it takes these two x's and then assigns to the same y value y1. So in other words, it's not one-to-one. But if you had a graph or a function that is slightly different, it looks like, so say you have three elements again, three elements here. This guy goes to here, this is assigned to that, this is assigned to that. So as you can see, this is a situation where output values correspond to exactly one input value. In other words, no y value goes to more than one x value. So that is the situation we call one-to-one. An important theorem about this is that if a function has an inverse, if and only if the function is one-to-one. So for a function to have an inverse, it has to be one-to-one. If a function is not one-to-one, then it does not have an inverse. So that's how we know if a function has an inverse or not. We need to always check the one-to-one relationship. One practical way of doing this is applying the horizontal line test. A function is one-to-one if and only if no horizontal line intersects the graph of the function more than once. To illustrate this, I'm going to use two examples. So think of y equals x cubed. We don't know if y equals x cubed has an inverse or not, but using this horizontal line test, I can know for sure. What I do is I just draw out random horizontal lines. We don't really care about what the equation for these are, just drawing out random horizontal lines. And then you make an observation. You take a look and see if any of these lines intersect the graph more than once. So like first line I drew only intersects once. This one, same thing, only once, intersects only once, only once, only once. So it passes the horizontal test. So it passes the test. What that means is that then y equals x cubed must have an inverse. Must have an inverse. That would be the conclusion I would make after applying this test. Similarly here, y equals x squared. So I draw first horizontal line. I'm realizing you pass here and here. Second one, similarly, it intersects the function twice. Because it intersects the function twice, then it fails the test. What that means is that y equals x squared does not have an inverse. Okay? All right. So now you may be wondering, okay, well, now we know how to find if a function has an inverse or not. Then how do we actually find the rule for the inverse? Like, what is more practical approach for finding the inverse functions? Earlier I showed you can take a look at specific rules and then you can undo the rules and then you can write out the inverse function using that idea. That is good, but it's not much practical in some situations. So if you like to have more practical approach for finding inverse functions, here's the steps. What you do is you write your function as y equals f of x, so you solve it for y, and then you solve this equation for x in terms of y. So you isolate your x value. And then what you do is to express the inverse as a function of x, you interchange x and y. So you switch x and y, and then the resulting equation will be y equals f inverse of x. So I'm gonna illustrate this on this example. F of x equals x cubed plus 2. So what I do is I write it as, first step, I write it as y equals x cubed plus 2. Second thing I'm gonna do is I'm gonna isolate x. So to accomplish that, I'm gonna solve for x. So it will be y minus 2 equals x cubed. I'm not there yet because I want to isolate x. I'm gonna to get just x instead of x cubed, I'm going to take the cubic root of both sides of this equation. So it's going to be something like cube root of both sides of the equation. And then I get cubes, and the cube root cancels out. So x equals cube root y minus 2. So the last step is you switch x and y. So then what you're going to say is then y equals cube root x minus 2 is the inverse of f of x equals x cubed plus 2. Or you can illustrate this as f inverse of x equals cube root x minus 2. So that's how we find inverse function. Another example, find the inverse of f of x equals x squared. So you realize x squared, as I illustrated before, fails the horizontal line test because it intersects like any kind of horizontal line above the x-axis will fail because it'll intersect the function or the curve more than 1 point. So well, then if I were to ask you to restrict the domain, what happens? Like, what if we restrict the domain of x squared? Because we know that generally the domain of x squared is any value from negative infinity to positive infinity. It could take any x value from negative infinity to positive infinity as an input. So then what we're wondering is, could we restrict the domain so that it has a inverse? The way we can do that is we ignore all the negative x inputs. In other words, if we only consider from 0 to infinity, so domain from 0 to infinity, this might work because, as you realize, this will pass the horizontal line test. So what I did is I restricted the domain of this function x squared to be only from 0 to infinity. So in that case, we can find the inverse because it passes the, I'm gonna note here, now it passes the horizontal line test. Okay, so now we know it has an inverse. But what is it? How do I find that function? Well, the way I find that is I use that practical approach that I just showed you. So I'm gonna find f inverse. So I'm gonna find the f inverse. So first thing I do is I write my original function as y equals x squared. Second thing I do is I solve for x. So it's gonna look like y equals x squared. So I need to isolate it. So I need to take the square root of each side. Oops, not the cube root. Take the square root of each side. And then here I will have, I'm just going to write it as square root equals x. And then the last thing I do is I switch the variables. So thus y equals square root of x. So what that means is that then f inverse of x has to be square root of x when x is from 0 to infinity, because that's the domain that I used. So therefore, square root function is actually the inverse of x squared. And then as you graph these two functions using a calculator, or if you just kind of try to sketch, you're going to realize that this is x squared. And then square root function actually looks like this. And as I told you earlier, inverse functions are always symmetrical with respect to y equals x, and you will realize that actually these two functions are definitely inverse of each other because they're symmetrical with respect to the line y equals x. Last example I have as following. The formula C equals 5 over 9 times F minus 32 expresses the Celsius temperature C as a function of the Fahrenheit temperature F. Find a formula for the inverse function and interpret it. In other words, this allows you to calculate Celsius based on Fahrenheit, but how do I calculate Fahrenheit based on Celsius? What if you had a situation where you have a Celsius degree and then you want to use this as an input to find Fahrenheit? So this could occur if you were to travel to Europe or like any other country that uses Celsius. What you would know is you would know the Celsius, but you wouldn't necessarily know how to calculate F, because this formula takes the input as an F and then it gives you the output Celsius. You need the inverse, you need the other way. And so the way we're going to undo this is we're going to find the inverse of this function. And so what we will do is, first we know that C equals 5 over 9 times F minus 32. We're going to apply the technique that we know. So we're going to solve for F. We're going to isolate F. So to do that, we need to first multiply both sides by 5 over 9, or 9 over 5. So what's going to happen then is you'll get 9 over 5 times C equals 9 over 5 times 5 over 9 F minus 32. So that is why we're going to cancel out, because this becomes 1. And then next thing we're going to do is, we know 9 over 5C equals F minus 32. I'm going to add 32 to the both sides, so 9 over 5C plus 32 equals F. Okay, so then what we found already is we don't need to switch the variables now because the variables were already given. Now we found the inverse function, so the inverse of the equation is essentially F equals 9 over 5 C plus 32. So if you knew this equation on top of your head, you can always switch going from Celsius to Fahrenheit. If you would like to simplify this equation, which is what I generally keep in mind, 9 over 5 is basically 1 over 8 C plus 32. So you can basically calculate, you multiply Celsius by 1 over 8 and then 1.8 and then add 32, and then you always get Fahrenheit's value. If you want to know more real world, like more practical one, you can actually use this approximate, which is more practical. So to approximate it, what I generally do is I multiply the Celsius, instead of multiplying by 1.8, I just multiply by 2, so 2 Celsius, and then I add little less than 32, I add 30 to get Fahrenheit value, which is very practical. So say Celsius value you have 7 degrees, I multiply by 2, 14, and then add 30, 44. So 7 degrees is approximately 44 Fahrenheit. So this is like a very practical way of calculating, which is something most people have no idea. Well, I hope you enjoyed this video, and thanks for listening.